Thank you.
You should have changed your title to the Enigma of quantum gravity.
Yeah, I know. But I had sent in the PDF, 24 hours ago. So.
Good morning, everybody, to our morning session. Today we have our first speaker today is Professor Renate Loll from Radboud University in Nijmegen, and the title of the talk is Quantum Gravity, Causal Dynamical Triangulations, and Quantum Curvature.
Okay, let me start by giving my heartfelt thanks to the two main organizers, Sumati and Madhavan, for having me and us all here. So it's a lovely place to be, and we're having a lot of fun. I hope is the mic on? It's not loud enough. It is on. It's fine. Okay, good. Let me find my clock. It reminds me that it's my mom's birthday today. Okay, later, Mom. Okay. So I hope my talk will have something for everyone. So those who've heard me talk about the subject before, and also those who maybe have not even heard of the approach. Let me jump straight in. I mean, these two pictures may get a little clearer as the talk moves on. It's kind of also traces a little bit the history of the last 20 or so years of that subject. So what is my specific perspective on quantum gravity? So that's important to set the stage. I want to construct a fundamental theory of quantum gravity, which ought to be non-perturbative, a diffeomorphism invariant, tackle dynamical geometry, and then study its property on Planckian regimes. So this will be bulk quantum gravity. It will not rely on boundaries or special reference objects I put into it. So this is really kind of attacking the heart of the matter. And of course, as we know, this presents major challenges, technical, physical, and conceptual. There are, of course, infinities in this, which are well known. We have to deal with the absence of a fixed background space-time. Devise appropriate ways of tackling it, describing it, and computing with it. And renormalization, of course, will also play an important role. And of course, as a cross-check, rederiving the classical limit, and ultimately, obviously, phenomenology. That's where we want to go. So in the program I'll talk about, or the Ansatz that has major progress in realizing this program is the CDT, or causal dynamical triangulations. I think of that as a minimal non-perturbative extension, quantum extension of GR. So it has already come quite some way, so it provides us also with a blueprint of what I would call emergence of quantum space-time, and taken quite literally. Of course, people use that often use it in a rather loose sense of the word, and also sets a stage for what kind of results can we expect to obtain in non-perturbative quantum gravity in a deep quantum regime. So what are the appropriate tools, and what is the nature of the results, and if you like, of the observables there. Now, why should you be interested in this? Well, you know, being here, you're forced to listen to some of what I'm saying. So it has already yielded results, and they're non-trivial and they're unexpected from a semi-classical point of view, despite the absence of any exotic ingredients, by which I mean, extra fields, extra dimensions, you name it. So one way of thinking about it is really also not just as a specific approach, but I would say it's been upgraded by virtue of the results we've gotten to a computational framework, which I think of as a lab more generally, where we're asking to make statements about Planckian physics. So, and this will amount to evaluating certain quantum observables, and of course, the beyond perturbations theory is a crucial ingredient. So you may think of CDT being to gravity what lattice QCD is to non-abelian gauge theory, namely to enable you to access a regime with fairly basic and minimal ingredients that you are not able to reach with other methods. So what is the demystification about? Well, this is less for this audience, but that for people who are only exposed to popular articles about quantum gravity, where the first line is always the amazing incompatibility between quantum theory and gravity. Well, of course, we are, of course, exactly addressing, we are showing that this is not the case, us collectively. And accommodating dynamical geometry, I think, is a good way of putting it. So you don't need more than just QFT, but you need to take care about the fact that geometry is not just an inert background. So, and what I also want to highlight is that, well, the mathematics that's behind what is in our GR textbooks is just not enough. And in a specific way that we've come to think about, also from the point of view of this particular approach. So there is beyond classical gravity in a specific way that taps into what mathematicians are actually interested in beyond classical Riemannian geometry. So there are actually ideas that have been borrowed from there. And there is this now, well, you can no longer call it emergent, but a whole mathematical field of so-called random geometry, which was born and motivated by developments in physics, but has also now become an independent subject. So here, of course, harking back is still a lovely quote from Riemann that is sometimes used. So he is, of course, the inventor of Riemannian geometry, but already anticipated back in the 1850s that, well, there may come a point where this, informed by the physics of the day, this point of view is no longer adequate. And we certainly have arrived at that point where we have to also, from a mathematical point of view, go beyond Riemannian ideas, or the Lorentzian version of Riemannian ideas. So in terms of phenomenology, I already mentioned, I believe, certainly in this approach, what is closest in terms of phenomenology, where we might be able to make a first step of linking the theory and what people call the real physics, is probably early universe quantum physics. So describing the very early universe in at a Planckian scale, and then by some magnifying mechanism, perhaps seeing still some trace of it in today's astrophysical observations. So, but what I'm talking about here is, of course, not quantum cosmology, so I don't apply any reduction, so it's kind of full quantum gravity, but nevertheless, likely implications are, I think, of a cosmological nature, to my mind, and also, as you'll see, that's where we're going. So just to recap, what on earth is the problem with quantum gravity? Why are we not there? Well, that's the main thing I have already emphasized, is the theory of dynamical spacetime, not on some fixed spacetime background. Okay, here my symbols got a bit entangled. So here we are not using, because that leads to a non-renormalizable theory, the perturbative split of the Lorentzian metric G mu nu into a flat eta mu nu Minkowski plus a perturbation H mu nu. But we go further. And the question is, of course, how do we go further? Because perturbative, relativistic quantum field theory is our standard method. That's what the textbook says. That what, that's what we use to describe the standard model. But as soon as we leave this framework, there is no unique way of proceeding. Yeah, so that's, of course, why I would say also for outsiders, maybe our field, it can be rather confusing because different people have taken different routes. So are there any examples of having gone beyond the perturbative regime within QFT? There are, of course. So a prime example is that of non-perturbative QCD, which we approach with lattice method. But of course, that has significant differences with the case we are interested in. Here, of course, where QCD does have a fixed background, and the gauge symmetry is entirely different, and the whole diffeomorphism story is not there. So the difficulties, of course, are many. As you know, we also don't have really experiments or observations to guide our theory building in any direct way. So it's also, even if our gravitational wave detectors become that much better, they will never tell us precisely where to look. I think we have to develop our theories further and make specific predictions and ask them to look in specific places for specific effects. So I think there is clearly work to do to bridge that gap from either side. So I'll be ultra short about the history of quantum gravity, which is, of course, long and glorious, or maybe inglorious. I'm interested in the non-perturbative part. So I'm characterizing kind of the up to 2000 developments, a lot about arguing what is the best approach, quite formal work we were doing then, not really emphasizing kind of so much of physics because one simply hadn't advanced too much in terms of the theoretical background. And there's a beautiful, yet another beautiful review by Steve that covers the developments of that time with emphasis on loops and strings. So I have recently written a little bit of an update emphasizing quantum field theoretic approaches after that era. So there is, one sees, around a renaissance of kind of the good old quantum field theory. I mean, in general, and also people working on string theory or maybe formally working on string theory. So one goes back, particularly to the covariant approach. I mean, trying to address quantum gravity as such, so not necessarily as part of a grand unified theory, but going back to a covariant quantum field theoretic point of view. Okay, so what is this formulation I'm talking about, the CDT, or causal dynamical triangulations approach? So it's based on elementary ingredients. So in terms of quantum theory, the superposition principle, so, or in other words, the path integral a la Feynman over geometric degrees of freedom. So of course, in the continuum, there is not so much wiggle space. Of course, you can use connections, but essentially, it's a. Let me stick to describing it as a path integral over metrics, modulo diffeomorphisms. So that's what the schematic Z means here, right? I have some measure. Here is a set of diffeomorphism equivalence classes, Lorentzian matrix, modulo 4-dimensional diffeomorphisms, and here I'm weighing each one with a e to the is, and S is Einstein-Hilbert or some other version of the gravitational action. So that's fairly elementary, and of course works in the rest of physics beautifully. So here the challenge is to give this a definite meaning beyond perturbation theory. And dynamical triangulations as an overarching notion is a realization of this very formal Euclidean, well, this is not Euclidean, this is Minkowskian, but this dynamical triangulations approach was born in a Euclidean signature, or that's where people first used it, and more specifically in 2 dimensions. It was really born as an approach to try and understand what's nowadays called non-critical string theory. So the dynamics of 2-dimensional curved world sheets beyond perturbation theory. So one triangulates these world sheets and then tries to perform an analog of the sum, but it can also be used, of course, just for the gravitational path integral as such. And so this way of describing, which I'll describe in a second a little more, of describing dynamical geometry nowadays goes by the name of random geometry and really signifies an area of mathematics these days. So the physics, the physics way of talking about it would be something like dynamic triangulations, or in our way, a causal a Lorentzian variant of this. So what you're doing here, so what's the essence in 2 dimensions? You work with flat equilateral, well, in 2 dimensions, triangles. In 4 dimensions, it would be 4-dimensional simplices. And in the Euclidean game, they are equilateral, so they are all the same. So you ask, where's the geometry, where's the dynamics, where is curvature? Well, it arises by gluing these things together in all possible ways. And the random refers to that, arbitrary ways. I glue these together, and each of them is say, in 2-dimensional curved geometry. And this is my way of regularizing the path integral, and I sum over all of them, and I take a non-trivial continuum limit as I make these building blocks smaller and smaller and takes their number to infinity. And then I try and understand, does it have a meaningful, is this limit meaningful? And in 2 dimensions, this can be still be addressed in a mathematically rigorous way. And if you want to read up on these developments, there's a beautiful article by Sheffield here. It's this archive article. So from a mathematical point of view, so many mathematical physicists and also physicists work on this subject. So this is 2D random geometry. This is Euclidean signature. So what we need in gravity, so these are the origins of how to think about, if you like, the gravitational path integral. So it's a new way of thinking about it. But of course, what we need in quantum gravity is number 1, Lorentzian signature. Number 2, we need it in 4D. And that's kind of the origin of the birth of CDT. And you see the first paper that Jan Armin and myself published on this is in 1998. And so making things Lorentzian in a 2D context can be explained in a rather straightforward way. So these are the building blocks of 2-dimensional random geometry as people practice them in Euclidean signature. So it's equilateral triangles, and you glue them together, okay? 2 manifolds. So not any wild gluings are allowed, but there should be manifolds. But of course, these can be fairly crazy gluings, when you look at them. So instead, in the Lorentzian game, we use Minkowskian elementary building blocks, which it turns out they are conveniently chosen as having both space and time-like edges. So I indicate this here in blue and red. And of course, you can only glue red to red and blue to blue. Yeah? In such a way, in the Lorentzian case, that an overall, it turns out that's important, an overall well-defined kind of causal or light constructor ensues.
Can I ask a small clarification question for the
Yes.
2D random geometry? So here, so is it same as you sum over all the genuses, and you sum over all the genuses?
Oh, well, that's an additional thing you can, it's an additional, the sum over topology is an additional thing you can ask about, and but no one knows how to do it. So I would say, there was a comment that also I made yesterday, even in 2 dimensions, of course, you can try and, well, there are ways of doing the sum in 2D if you include the sum over genus, for example, but there is not a unique way it's non-Borel summable, but there are, of course, ways of summing up those things. And people have suggested various ways of them, but no one, this is, of course, work from the late 80s. Even in those days, people couldn't come up with a good physical motivation, to choose any one of them. In higher dimensions, of course, the problem is much harder. So we can talk more about topology change, but I would say, of course, someone clever may come about or arrange keeps the eye in and arrange for cancellations to occur, but no one, it's not doable with standard methods. Yeah, it's an interesting topic in itself, I would say.
I have a very basic question.
Yeah.
On the previous slide, so when you show this 2D random geometry, right?
Yeah.
It looks like the surface itself is embedded in 3 dimensions.
No.
No? Am I seeing it incorrectly, or just?
Yes. Yeah. For the sake of showing them and showing you beautiful pictures,
yeah.
That's correct. That's a typical. Yeah. Thank you anyway for pointing me to the picture, because I wanted to comment on it. No. The geometries are intrinsic. But in 2D,
Right.
you know, of course, we cannot show them isometrically, but this is just to give you an impression in 2D what a typical member of the path integral looks like. So you see they're very non-classical. And that's part of the that's part of the game. And that's part of what you would expect in quantum field theory anyway. Yeah.
So you're not restricting the triangulation to be planar, right?
Well, this is, you know, typically in all this game, you know, some fixed topology is chosen. This happens to be a two-sphere. Later on,
Okay, that was my question. Okay.
That's a choice. It's a choice you make. And of course, you know, if you go for large triangulations, and if you're interested in bulk properties, the global topology, you know, for certain local quantities shouldn't matter all that much. But a choice is made here, typically. Yeah. So what?
What was the classical theory? You're saying it's very non-classical, the stuff you get. So what was the classical theory for 2D?
No, I'm just commenting. This doesn't look like a nice
Manifold.
Yeah,
okay.
yeah, yeah.
Okay. But the action will be something like area or something, right? I mean, I don't know what
Yeah,
the
yeah, this is just
the
is
toy.
in 2D, it's just a volume action because, of course,
yeah,
R
yeah.
is a topological term. But typical in that ensemble weight with just the volume, this is what comes out.
Thank you.
But in higher dimension, it's this, you know, nova differentiable objects. So these are direct higher dimensional cousins of the nova differentiable path of the Wiener measure that was, Faye mentioned already in her talk yesterday, in one-dimensional quantum mechanics. But so here we get higher dimensional geometric realizations of rather similar ideas. And also you should expect rather similar, you know, wild geometries in the sense of these nova differentiable things. So that's a feature. That's not anything, you know, there's nothing wrong with that. So discretizing and regularizing quantum gravity has a long history. So in the 50s already people, you know, thought about just putting things on square lattices. This became more of a big game in the 1970s because with a big boom of applying lattice methods in QCD, say, which had come up with first, you know, successes, and of course by now is an amazingly successful way of understanding the non-perturbative properties of QCD at low energy, including the spectrum. So I would say if you knew as much about quantum gravity as people have learned about non-perturbative QCD using numerical methods, we would be in much better shape than we are today. Okay, so what is the general strategy? A lattice structure acts as a regulator. So with some cutoff, so length cutoff, yeah, which is the lattice spacing or the UV cutoff A. So in our case, it will be the typical edge length of these triangles or simplices. One searches, so of course just discretizing things, it doesn't give you anything in terms of a theory. So as I have already emphasized, a continuum limit is an important thing to show to exist. So what does that involve? Certainly in higher dimensions, it involves, of course, renormalization. So when you write down the path integral in your discretized framework, you know, you will have a bare action which contains bare coupling constants. And of course, these will get renormalized, you know, in the process of getting rid of quantum field theoretic infinities. So it's a standard, it's just a lattice version of standard things we also even do perturbatively in quantum field theory. So, but here in this lattice formulation, what in addition you have to look for are second or higher order phase transitions in the phase diagram of the theory. So the phase diagram is just spanned by the bare coupling constants of your lattice theory. What happens near a phase transition is typically some correlation length diverges, and that enables you to take the limit A go to 0, accompanied by appropriate renormalization of these coupling constants. And in that limit, you can show that details of if all goes well, details of the regularization get forgotten. So you evaluate kind of all your formulas in an asymptotic way, and that gives you kind of in the approach to this critical point, that defines for you the continuum theory. Now, so universality is a critical notion here, and it's not the same as discrete quantum gravity, where you just You start with some regularization, and you postulate or a discrete formulation, and you postulate that, you know, some short distance is just to be identified with, you know, the Planck length or some small integer times the Planck length, and then you don't take a limit, right? What you then also typically use is this mechanism of finding a universal continuum theory. Right? Then you have to argue, of course, which of all the possible discrete choices, why did you choose that one? And these choices will typically make a difference for Planck scale results, if you're interested in those. Okay? So as I said, this is a long-standing game. So that's a uniqueness. I mean, if you follow kind of this way of arguing in terms of, you know, critical systems looking for these transition points, then, you know, a continuum theory, if it can be shown to exist, has uniqueness properties typically. Now, as I said, since the 1970s, people have followed this basic idea, just also emulating the successes of gauge field theories. One started out with first-order formulations of general relativity to make them look as much as possible like Young-Mills theories that even predates Ashtekar, Barbero variables, which are connections, which also lend themselves more easily to, you know, a quantization on a lattice with one-dimensional links. These were studied in many different formulations on lattices, and also simulated, but no interesting results were seen, ever, there. And it kind of, this ran out of steam, and it is a little bit unclear where to point to because there are so many problems one ignores. The biggest of them, the biggest elephant in the room, is that diffeomorphism symmetry is badly broken when you put just GR on a fixed lattice, because it just nowhere, where has it gone? So are you even quantizing the right, you know, correct number of degrees of freedom? So this is where this approach kind of stopped. Then there is so I call this a naive lattice quantum gravity. So the not so naive lattice quantum gravity builds in the diffeomorphisms, or rather the structure, the dynamical aspect of the geometry in a more intrinsic way. And it's based on this old idea of Regis from already 1961, exposed in a paper that is called GR without coordinates, and that highlights the essential property of this formulation. So in the continuum, you have a formulation of a smooth manifold M and a smooth metric assignment, or at least, you know, twice differentiable metric assignment of Lorentzian metric. This is substituted in Regis' formulation, in this piecewise flat formulation, by a triangulation T made up of internally flat d-dimensional building blocks, 4-dimensional, of course, for gravity, where our free variables, our dynamical variables, are the edge lengths of these triangles or simplices. Yeah, so here's a little example in 2 dimensions. So you're free to choose the L's, or rather the L squareds. Why do I use L squareds? To be able to accommodate any signature. So this works, this idea works in any dimension, in any signature, yeah? And, well, is subject typically to triangle inequalities. So the path integral, if you wanted to use that in the quantum theory, so there is something called quantum Regge calculus, it would be an integral over the L's with some measure subject to triangle inequalities. So it's a quite tricky thing to realize, but people did study a quantum version of that. The CDT implementation is different, as I just explained. So here, essentially, so if you're in a Euclidean version, the lattice edges are all the same. And the way you realize the sum of all geometries is by summing over all possible gluings, subject to manifold rules, but the edge lengths, they stay as they are. So you don't have any more continuous variables that parameterize that space, but it's these gluings. Yeah? So, and it's generally different, both in the setup and also in the results that have been obtained to quantum Regge calculus. So here, that's the random geometry, back to the random geometry idea again. Your building blocks are essentially trivial, so pieces of flat space. Okay, of course, they can be glued together in such a way to pick up intrinsic curvature. So that's, of course, crucial, because we're not we're not talking about flat spaces, but the edge lengths are not involved. They are basically fixed.
Can I ask a small
Yes, of course.
So in the usual lattice, these three case, I mean, when I denormalize, I start scaling A and
Yes.
that is up. But here, I mean, scaling A is some of the numerator.
Yeah, no, A is a Judy's, is a proper length. Yeah. Thank you for the question. So I would propagate. To deal with the dynamics, well, you should do this not so naive way, and the approach that arguably has come furthest in this is the CDT approach. So let me just flash the ingredients. This is again our formal path integral. So let me just restrict myself to gravitational degrees of freedom. So this, let's for definiteness choose this, but this in actual examples, that's what we are also using, is the Einstein-Hilbert action. So there is a cosmological constant term. So we have G Newton and lambda. And now we discretize this, and for the discretization, we use, is a non-unique prescription. We describe the action in terms of the length variables. And since the lengths are essentially all the same in dt and cdt, this becomes a very easy kind of counting expression, counting building blocks of certain types. So the 1, the 0, the 1, and the 2 simplicity. So in flavor, it's not all that dissimilar from the causal set action that was written down, but it's actually, it is a local or quasi-local thing. So that's our action. There's a very simple measure factor, which one can argue is very natural, which involves that the C of t is the order of the automorphism group of a given triangulation. That means should a given triangulation accidentally, I would say, have non-trivial maps that map it onto itself, preserving all the connectivity, then you divide out by that integer. Okay, so you can argue that's a good analog of the de Wit measure in the continuum. So again, we're not interested in finite triangulations. We are only interested in, is there anything meaningful when we send n, the number of building blocks, to infinity? And that is typically done by keeping a physical volume, which I call V, fixed, and finite. So we, of course, when we go on the computer anyway, we are only able to simulate finite volumes. So n times A4, this is now in 4 dimensions. That would be the typical what you keep fixed when you either send A to 0 or equivalent when you fix such a volume, send n to infinity.
Renata, just a
Yeah.
quick question. The C of t that you have there, what is so these are symmetries of the triangulation.
Yeah.
But in the space of possible triangulations that you have,
Yeah.
how many of them would be symmetric? I mean, this factor would typically just be...
This factor is almost always 1.
Okay, great. That's very similar to causal sets.
Yeah.
So maybe I just ask a small question.
Yes.
In the first equality, typically Z will be a function of the asymptotic data, like Z, because when we do path integral, the continuum path integral, you have to...
Well, I decide to put myself on continuum path integral where M is just a finite chunk of space-time.
Right, but should you not have whatever your finite volume is, isn't there some boundary condition you would put on the...
No.
equilibrium?
Look, I choose spatial boundary conditions to be periodic, so that could be a 3-sphere or a 3-torus. That's typically what we use. And even in the simulations, for convenience, as a matter of fact, we choose cyclic boundary conditions in time.
Oh, so you don't have a boundary?
No, there are no boundaries. So this is really the essence. This is pure bulk. So what is special about the CDT compared to the Euclidean DT? So
Can I ask
the building.
quick question?
If I have very many questions, sorry guys, we have 1 hour of
This is a
discussion
very, very
afterwards.
quick question.
Yeah,
It won't take long.
it better be a very good question.
Yeah.
Sure.
I don't know if it's a good question, but it's a quick question.
Yes.
Are your simplices in dimensions greater than 2, are they all the same shape?
Depending on, I have 2 edge lengths in the Lorentzian game, so 1 fixed time-like edge length and 1 free spacer edge. So in 4 dimensions, we have 2 different types. I mean, apart from rotations. Yeah.
No, but what I'm saying is, can you construct a tiling, let's say, of 3
Perhaps we
dimensional-
can leave the question for the discussion session. And
Okay.
Let's move
yeah,
on.
there are many.
But thank you,
You know,
for that.
so I have to take a bit of a shortcut, to get somewhere. But please ask me all of these questions. I mean, they're all excellent questions, but let me try and answer them, after the talk. So, what distinguishes the Lorentzian game? It's not just the different building blocks, which are Minkowskian and not Euclidean, but the way we glue things together. I kind of highlighted this a little bit. So in CDT, the spacetimes you're summing over in this path integral obey a kind of a discrete version of global hyperbolicity. So what does it mean? It's one way of putting it is to say no topology changes of space are allowed as a function of time. So you cannot have, kind of trouser topologies where, one arm of the universe branches here and the other, to the other side. So that's not allowed. And the way we enforce it is by arranging the geometries in kind of layers of kind of proper time, if you like, proper time, one step in this discretization, where you can think of the four-dimensional geometry as consisting of very non-flat, three-dimensional objects, and the interpolation is done by my four-dimensional elementary building blocks, simplicial building blocks, to get from one step to the next. And so you can think of this as a stack. So these are not, don't be misled, these look here flat, but of course they're not. They're kind of, crazy and wild, these so-called spatial submanifold. But it's handy, so there is a notion of time that comes in here. But of course, this is just a discretization. It has no physical meaning. But what we discover is that in the continuum limit, we find interesting observables where on cosmic scales, this plays a role of cosmic proper time. So that it was after a posteriori, at least on global scales, you can give it a nice physical interpretation. One of the, en passant, one of the things that emerge, that transpire from playing around with these triangulated models is that people, of course, started in the Euclidean and said, of course, being aware that this is not the physical thing, but one could, argue, perhaps, following people like Hawking et al. In the continuum that, some time or causal notion will, in the Euclidean path integral, will emerge dynamically. Unfortunately, we don't know of a single example where this has ever happened. And then you find that the only other way, we poor people could think of is to put it explicitly in the building rules. And the lesson is that if you do that, then you get a totally different result. So in particular, in 4 dimensions, you do get a result that's much more interesting than what people previously found just using Euclidean. So what do we do in CDT? We generally start from the complex expression for the path integral. The I is there, and we're summing over discretized Lorentzian geometries. Then it so happens we do have a well-defined, on the level of these regularized geometries, Wick rotation. It's an analytic, is a very specific analytic, is a precise mathematical prescription, an analytic prescription in a parameter, one of the parameters that is floating around in this discrete description. If we analytically continue this in the right way, we do obtain exactly kind of the expected for the action, the expected Euclidean path integral expression. But of course, what appears here then is not the sum over all Euclidean triangulations, but only those that I got by inverse taking this Wick rotation map from my Lorentzian spacetimes. And it turns out that this restriction is at the heart, the different configuration space that you get this way is at the heart of then producing totally different results. So there is this Wick rotation. It's something that is not known. There's no continuum analog known. There is no node. There's no coordinate redundancy. This is already, the old Reggie idea, if you like. So only geometrically distinct objects are summed over, and essentially in a democratic way, apart from this small 1 over c factor. Each one is in that sum with some weight, and then we try and do the sum. In 2 dimensions, we can again do it analytically. So we have a beautiful analytically solved model. In 3 and 4 dimensions, we cannot, and of course in 4 dimensions. So we have to rely on numerical methods, and for those numerical methods, the existence of the Wick rotation is essential because we use Monte Carlo simulations where we need a probability distribution, which we only get if this is an e to the minus s. but that we get by applying the spin rotation. So, so what I also want to emphasize, although this looks kind of this slicing structure, is initially conjectured, oh, it must have something to do with Hojarva-Lifshitz gravity. In 2D, the two things, Hojarva-Lifshitz and CDT and other formulations turn out to lie in the same universality class, but there's no indication that this happens in 4 dimensions. So here we are. What?
There's no definitive argument either.
No, but there are very good other arguments which we can go into after the talk, if you like. Yeah. Which make it, well, we actively looked for what it could be, but there is no indication currently that it is. So, so I have a computational framework, so what can I do with it? I sold it to you as a method to get to numbers that are interesting from the point of view of quantum gravity. So what are those numbers? Well, essentially, the quantities we look at are quantum observables, operators that we insert into the path integral, into the trace, if you like. I just write the formal continuum expression for definiteness. This is now Euclideanized, and normalized. And we are interested in the expectation values. If my two boundaries are far enough apart, this will be like vacuum expectation values in the bar, if you like. So that's what we look at, and we can study numerically, because the framework lends itself to that. Now, note, so there's one health warning is, of course, as we know, if you don't put any reference systems or matter then into the system, then diffeomorphism invariance really dictates that my observables tend to be very non-local. The theme of observables has come by a little bit in the context of relational observables, but the typical things one can relatively easily study here are of the form of non-local integrals over some scalars. So R of x is, of course, in that context, is not really a good observable because it refers to a specific point, and I have no idea how to single out a specific point in my sum over geometries. Where's that point x in this next configuration? But of course, this integrated object is a perfectly well-defined concept. Now, obviously, that takes us away. I mean, typical observables being of a quite non-local character, that just takes us away from questions we often ask. We wish that quantum gravity would solve for us, which are often, we formulate, they come from semi-classical or even classical questions, and therefore, typically refer to local structure. You can already get an understanding that structurally, this will be not easy to answer, or maybe impossible to answer, but that has nothing to do with my specific approach, but it's just in the nature of the beast. So it's a feature rather than well, it's an issue rather than a problem that presents itself, in a specific framework. So that needs then, expectation management. So, people ask, can you solve blah, 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 my favorite problem X, and it will also have to do something with, the entropy of the horizon. Well, give me a nice non-perturbative observable that captures exactly that property you're after, and let me see whether we can actually, implement it in that path integral formulation. So that's also something I can talk a long time about. I will not do it here, but just again highlight it as a health warning of what to expect. So are there any interesting things we have already learned? Yeah, so I want to point you to what I would call a quantum signature, right, that we found in the context of CDT, and this is this interesting reduction, dimensional reduction. So if you study the spectral dimension of your space-time or your quantum space-time, the spectral dimension is a notion of dimension that characterizes a diffusion process. And it's a notion of dimension. Of course, you can apply, let's say, locally on a classical space-time. It will always reproduce. So you basically let an ink drop fall into your space-time or your fractal space. It can be anything, and you monitor how this ink drop grows as a function of diffusion time, and that gives you a characteristic kind of power law to leading order, and this is related to the spectral dimensions that you extract this way. And we can measure this on the ensemble of spacetimes in CDT in the path integral, and it was found to be compatible with a large-scale limit of 4, which is good. It's a classical expected limit, but on short scales is a vicinity of 2. And that is something that has then subsequently been found as a perhaps universal phenomenon, as Stephen has conjectured, across other approaches. So it's a prime example of something you cannot see in perturbation theory, but it was found here in this non-perturbative approach. And then you can say, okay, maybe that's an interesting, we have very few observables, right? This is one of our problems in quantum gravity. We don't really know how to compare nodes, but this is now a concrete type of observable where we have been able to do that and draw also some conclusion from it. But of course, to understand full 4-dimensional quantum geometry and quantum gravity, one must go beyond dimension. Okay, so here is a key result that I alluded to in my introduction, that of emergence. So we cannot say, so we have this path integral. We studied in the computer, and what means, of course, it doesn't talk to you, you don't know what that superposition is. So what you do is you evaluate specific observables. So you ask questions to that system, and then the outcomes give you some partial information. The more observables you have, the more information you will gain about that system. So one cannot really, in such a framework, or I would say maybe even quite generally to say, one recovers the classical theory, because the classical theory is a whole edifice, right? It's all of GR. But one can look at certain observables which one has access to and check, do they have a classical limit that coincides with my expectations on large scale? And of those we have a number, several. So one of them is the average, what I would call the average shape of these, of the quantum geometry that comes out. So it's a spatial volume as a function of the proper time that comes with this description. And many years ago already we showed that this shape, this is a topology of S3 cross an interval, time interval, can be beautifully mapped on the shape of a, of course, Euclidean de Sitter space. And so here is the measurements that come with it. So this is here my proper time. This is a 3-dimensional, the expectation value of the 3-dimensional volume. And you see this beautiful curve here. And you cannot distinguish the cosine cubed curve that is characteristic for the continuum de Sitter space from the measurement data. These red things, they are not error bars of our measurements. They are the typical size of the quantum fluctuations of the 3 volume around the mean. So what you can see here, there are sizable quantum fluctuations here. This is only possible because the universe we are actually looking at is tiny. It's like something like 20, 25 Planck lengths across. So that is why, yeah, the global volume still quantum fluctuates appreciably. Yeah? So it also, we have also analyzed the waveforms of the low-lying spectrum of these excitations, and they beautifully also match a semi-classical expectation. So here one would then say, so we've rediscovered de Sitter, but that's just not the case. This is just a single variable, and we've matched it to a semi-classical expectation for long distances. But there are, of course, many, many de Sitter. I mean, it's just a space-time, so there are, in principle, many modes. So the next thing we were looking for is there a way to attribute curvature to a space-time like that? And that's a highly non-trivial thing to ask, because we are sitting in this totally non-differentiable quantum regime for the individual geometries. So it's not even clear that the notion of curvature exists. But we found one, and we have found additional evidence that on large scales and in an averaged way, this wild quantum universe, whose shape we look at here, also has curvature properties that can be mapped onto that of or rather are compatible with those of a constantly curved de Sitter space. Not in any local sense, because in a local sense, these things are still crazily quantum fluctuating. So let me say a few things about curvature and then kind of cut to the end, because I'm running a little bit out of time. So what about curvature? Why does no one talk about curvature in quantum gravity? Well, of course, you don't get very far in talking about quantum geometry in 4 dimensions at all, but you can ask the question at at a level, of existence. If I have a simplicial manifold like the picture I showed you, or a causal set, like several of my colleagues have already talked about, or something, people think about, describing quantum gravity by some discrete structures like graphs. Can I associate a curvature with this? Is a priori absolutely unclear whether I can and whether that makes sense at all. Ultimately, of course, it's also a physical question. One way to phrase the question is, of course, curvature is an absolutely essential ingredient of how we think about classical spacetime in GR. Is it possible to get away without a quantum? Should there be a quantum analog? Or is that, again, something emergent? So we've answered the question by explicit construction, by creating a notion that, well, clearly will not be unique in the quantum context, but converges to something known, the known thing in the classical theory. And moreover, it turns out that it's a very hot topic in mathematics. I mentioned earlier, people are looking beyond Riemannian, pure mathematicians, and looking for new ways of, in particular, Ricci curvature is a big game in that context. So there are conferences. I was not too long ago at the Fields Institute for a conference where just people were talking about generalized notions of Ricci curvature. So actually, the curvature we've been introducing in CDT is motivated by some purely mathematical works that comes from that. Of course, then adapted to the quantum context, which is even kind of crazier than what those people think about. But I just wanted to point to the idea that, in math, purely, intrinsically, these ideas have arisen. And at the same time, within quantum gravity, we find a similar motivation for looking at the very same thing. So why, you might ask, are things like the deficit angle that we inherit from Regicagus, why are they not good? It turns out that in 4 dimensions, that's an experimental result. In these partition functions we were trying to sum, these expressions diverge uncontrollably, in the sense that we don't have any good precision of how to renormalize them. So it's, of course, even in the continuum, obviously, curvature is a differential operator. So we expect to have to renormalize it. But the question is, how are you supposed to do that? And this new notion also kind of does it implicitly. I can only give you a super brief account of what we do. So how do you measure the curvature of a space that's not differentiable? And the only thing you have available is a notion of distance and a notion of volume. So here's the way that we've stolen from Jan Olivier, that's a mathematician. It works in Riemannian signature. So it will work on the big-rotated geometries of my ensemble. So what you do is you take 2 geodesic spheres of a certain radius, epsilon. You make sure that their distance, the distance of their centers is delta. And then you measure the distance between the first geodesic sphere and the second geodesic sphere. So you have to take your favorite notion of distance of an extended object. So what we used, it turns out to be not, for our purposes, not to be very crucial what to use. We're using an average distance where, well, first of all, we set delta equal to epsilon, just for simplicity to have a single scale around, but then compute the average distance of any pair of points on these 2 spheres and normalize it by the individual sphere volume, and then we get something we call the average sphere distance. But which notion? The mathematicians use different notions based on optimal transport. We use this notion because it's relatively easily implemented on the computer. So what is the key idea, the key geometric idea? If you can do this also on a classical Riemannian space, and what happens then if you make these small enough, so that no funny things happen with your spheres and your geodesics, then you can show that on a metric space with positive Ricci curvature, associated with this direction, this vector here, the distance between the 2 nearby spheres is smaller than the distance between the centers. And conversely for a negatively Ricci curved space. So here you have a concrete, what is the beauty of it? There are no geodesics involved. I just have distance measurements and volume measurements, to be able to determine the volume of the spheres and to make this comparison. So to cut a long story short, so this is the notion of curvature. You see, we implement in the quantum theory. And you see it comes with a scale, which is the scale of the size of the spheres. Yeah? So what we do, which is also very helpful because we are interested in the notion of curvature that I can let depend on a scale. On short scales, I expect it to be nothing like what I would expect classically. And on large scales, I can ask, is there a classical limit that I recognize? And that has something to do with the classical way of doing this. So I'm cutting that story short. So you can make a completely detailed, in the classical case, a comparison. You can write this down in Riemann normal coordinates and do an expansion. So basically what one does, one takes a quotient of the sphere distance and the center distance. Yeah? In a flat case, this would be a constant because the sphere distance would be equal to the center distance. But in the other two cases, one either gets a positive or a negative correction term. And if you like that correction term, we call the quantum curvature. Yeah. So again, it's a long story cut short. But if I monitor this quotient on classical constantly curved spaces, you see very clear qualitative differences. On a flat space, this is just a flat. It's just a constant term. On a sphere, it goes down, indication of positive curvature because we define this here with a minus sign, and conversely on hyperbolic spaces. So why is this important? Well, we do a computation in the quantum regime, and we need to compare it to something. Yeah? So what we do in the quantum regime, we evaluate this prescription on various scales. This is as a function of this delta scale. We evaluate it and compare it to what we know. And then we try, can we draw conclusions? So we've done this for toy models. It works in 2D. So this is a Lorentzian, typically two-dimensional space-time. This is kind of this candlestick thing. And this is a typical Euclidean type, which I had already flashed on one of my previous transparencies. So this is Liouville gravity. Yeah? So what we can do now is associate a curvature in an integrated way. Again, it's an integrated quantity to make a diffeomorphism invariant, but it depends on a scale. So there's non-trivial scale information. So what we find here, our tori, our quantum tori for 3D in 2 dimensions, these are increasing volumes. You see finite volume effects. It's this curvature here. These are the initial thing you should cut off. These are lattice artifacts. So it's not, the torus is not flat because that would be a horizontal line, but it has this slight inclination. We don't have a very good interpretation of why that is, but this is quantum geometry for you. In 2D, we find that the curvature of this object, Liouville gravity object on an S2 topologically, can be mapped beautifully. Well, the first results, going back to 2008, was the curvature profile of a continuum 5-dimensional sphere. We have recently redone that, and it could also be a 4-dimensional sphere, which accords more with one's expectation, but this is something I could go into. So what is this important? Well, we wanted, of course, our main interest was the 4-dimensional case. So we did it there. And we could, of course, even on very large lattices, so these have hundreds of thousands of building blocks, of course, the quality of your data is, of course, limited by your numerical limitation. So what we find here is a quite similar picture to the 2D case, but the quality of the data is not as good. But we can still, if you compare to a continuum 4-sphere, that volume profile for our dynamically generated quantum universes in full 4-dimensional quantum gravity shows definitely that there is a kind of positive curvature, and we can also map it reasonably to those of a continuum sphere in a certain range. So this gives you a flavor of what we can do. So before wrapping up, so what is this curvature? What else is this curvature good for? I could talk for another hour. It opens a window. It's a first. Well, this, curvature is of course ubiquitous classically, but having now a reasonable notion, quasi-local notion of curvature, we can use that in other observables. And we can use it, for example, in what we call homogeneity measures. So what else is interesting, what I could ask of my de Sitter universe? Is it actually homogeneous and isotropic in some coarse-grained sense? So we have now developed non-perturbative quantum measures of homogeneity. We have only tested them in 2D, but one could and would like to apply them in 4D and ask something like, well, is the curvature, how homogeneous is that? So what we do is basically we cover the space by geodesic spheres, integrate our curvature notion in those spheres, and then look at the statistics of those, and then make the spheres bigger and see whether we see some convergence. So another thing we can do is study two-point functions. They have been studied extensively also in the old days in DT, but one never had a good notion of curvature. We have this now, and we've tried it out in 2 dimensions again as a proof of principle. So we have a curvature correlator, so called a 2-point function. It's because our notion of curvature is slightly non-local. I indicate this by these 2 spheres. But this is R, this is a distance R. Here we normalize by the lattice units. So what we see here, beyond a region of lattice artifacts, curvature correlator is absolutely flat. So this is what one would expect, because there are no propagating degrees of freedom. Of course, the challenge is to do the same thing in 4 dimensions. There are a lot of subtleties with these correlators in the non-perturbative theory. They cannot compare it one-to-one with corresponding, perturbative objects. To summarize what I've said, so characterizing my way, the way I've presented, you could think of it as computer-assisted construction of a quantum gravity theory. So somewhat analogously with QCD. So we are getting definite new insights from these quantitative studies of the strongly coupled Planckian regime. I warned you, I gave you some health warning in terms of expectation. What can one expect such a formulation? And I would say also any other formulation of quantum gravity in the deep quantum, what can I expect them to deliver? Observables of a certain type, quite non-local. Here one is looking as a strategy for universal properties and new quantum signatures that one might be able to address in other ways. So there's something rather than nothing. So we have already concrete results, so switch dynamics, and I've also highlighted that there is definite new mathematics that is in the background. Of course, it's as usual in higher dimensional quantum field theory. That's what we need in physics. But the mathematicians who are always a little slow to deliver on the 4-dimensional case. Here she's come. So I said CDT, I think of that as a computational tool, so minimal non-perturbative quantum extension, and there is definite way of talking about emergence of certain aspects of classicality, looking at suitable observables from this quantum space-time, which we've constructed from first principles. So what's beautiful is there is a relatively clear path ahead what one wants to do next. One wants to identify more properties of this quantum de Sitter, this candidate, I would say, for early universe description. What can I say about the fluctuations? And what can I say about 2-point functions? And in reasonable ways, can I relate this to very far away results, say, from QFT on curved backgrounds? And there's structure there. So thank you very much. I hope I've given you a good idea of what this is. A couple of reviews I highlighted here. Thank you.
Hi. So maybe I had a small question about the volume expectation
Sure.
value. So you have fluctuations which are, the fluctuations are Planckian, right? In the
Yeah.
you show the spread.
You mean on the
Yeah.
de Sitter shape?
Yeah, on the de Sitter shape. But
Yeah. So the whole universe which you saw there is, I said, like 20 Planck lengths across, so you can.
yeah.
Yeah.
But then there are, in principle, there will be non-perturbative corrections to the. Are they not? Somehow I couldn't understand.
No, the whole thing is already, of course. This is what I'm presenting you are
Yeah.
properties of the non-perturbative ground state of the theory.
Yeah. So what I mean is like 1 e to the minus 1 by G Newton times correction to the.
Well, yeah. So what the only thing, the shape, the shape had tails. So and if you ask for, so what we are plotting is basically the scale factor as a function of proper time. So in the tails, of course, there we can write down an effective action for the scale factor, which we reverse engineer from our computer data. But when it comes to small scale factors, where one could then look for correction terms, well, our resolution is simply not good enough.
Nice. But because you have global hyperbolicity,
Yeah,
I
yeah,
thought
but you can. But what we do see is that is a stable ground state. So whatever corrections there are, kind of for small a, you know, they're hidden somewhere. I mean, as I said, you know, the fluctuations, we can characterize that spectrum, but going further is with current resolutions not possible from this effective action.
I mean, some instance corrections you have suppressed because you have this global hyperbolicity requirement, right? Or somehow, I thought that.
No, I don't. There's no relation with suppressing any.
Okay,
Yeah, yeah.
in 3D, I think.
So I have another question. So this shows how the sitter emerges. Can one see something like black hole spacetime emerging this way? Is there? So why is it just the sitter? It's
Yeah,
a very silly question.
No, it's not a silly question because, yeah. So what is the question I'm asking here? Of course, I'm putting in some boundary conditions, if you like.
Mm-hmm.
So but those are basically the topology I've chosen, right? And well, basically, you know, that's more or less it. So and of course, I could have chosen to have open boundaries.
Mm-hmm.
Yeah. But so what I've chosen is with my choice of boundaries, which was actually a cylinder. So it's an S3 cross S1.
Mm-hmm.
So the interesting observation is that dynamically, this actually wants to be an S4.
Right.
So this is one observation. So one can then ask, of course, a question, you know, we've asked for a long time, is it possible? So this is the ground state, kind of the non-perturbative ground state, if you like, of quantum gravity in some sense with those conditions. Mm-hmm. So what happens if you change things?
Right. So for a black hole, you would have to have different boundary conditions.
Yeah, right. It's very, no one has thought, well, we thought about it, but there are no reference point. One would have to have open boundary conditions, you know, because this is a finite,
yeah.
You can only do finite volumes, and then something would have to be told to these boundaries. But of course, there is, you see, there's of course absolutely no reason why, we don't know, right? Why you give an arbitrary solution to Einstein's equation, I could realize it as a ground state of a non-perturbative path integral. I mean, this is, you know, basically unknown territory. We don't know.
Okay,
whether this is even realizable in principle with a clever choice of boundary conditions. We don't know.
Thank you.
There's another question by Abai.
Yeah. So, I mean, just to continue, it's
Yes.
a slightly different question. But then, I mean, you know, first of all, this is really, what you're getting is force sphere. When you call it the setup, it's a force sphere,
Yeah,
right?
that's correct.
Yeah, so it's a force sphere that's what you get. So I'm not clear that anything in the intrinsic approach that you have got tells me that I should interpret this as de Sitter because I don't have a notion of Wick rotation in the final limit or something like that. So I don't know in what sense is this really a de Sitter?
Yeah.
In
So
the
in the
hyperbolic
following sense that I put in a time parameter, and which I emphasize is not a physical parameter, but of course it you know, in the sense that these of course are very non-classical geometries already, you know, before I take the continuum limit, it's something like a proper time parameter. So if I take this and I renormalize this suitably, then I can simply map the line element which I flashed, the volume profile I get from the standard Wick rotation Euclidean line element of de Sitter. I can just match this to my observations, and therefore I say it's a very natural interpretation. So more one cannot say.
And then what is it that determines the value of this constant C? Because I mean, there's a cosmological constant somewhere.
C? What is C?
In the metric you wrote down dt squared plus C squared cos squared. I mean, what is the value of the cosmological constant? If it's de Sitter, then I should know what the value is.
Yeah. So here it's determined. So these are all the simulations are done for fixed space-time volumes. Yeah. So the C will be related to the volume. So lambda is a Lagrange multiplier because that's how we can do the.
But is that physics? I mean, I want to emphasize that I'm really deeply, deeply impressed by the progress that has happened
Yes.
here. And as you say, that there is, there's limits on how much numerics you can do, because the radius of these de Sitter space-time is still Planckian, right?
It is Planckian, yes,
Yeah.
that's right.
Okay. So, I mean, would like to get macroscopic thing. There are many things they would like to do, but of course, limited resources and so on. So that's not my,
No,
my
but
point.
the essence of the thing is, of course, this is a unique gateway to exactly the Planckian regime. I cannot, in this technology, even if I wanted to, I cannot do macroscopic universes with the parameter space I can map out. It doesn't seem to be possible. So so I cannot realize, the limit on the lattice. I can, of course, extrapolate certain
Maybe I'm
things.
taking
Certain
too much time,
observations.
so maybe I should stop. Give it.
It's not on.
Is it on now?
Now, yes.
You have a notion of the quantum Ricci curvature. So
Right.
is there also a microscopic notion of geodesics, and does it give the GR ones in the continuous limit?
No, I've actually, because geodesics came up in a previous discussion, they are not very well defined as objects, because at least not as solutions to differential equations, because anyway, I'm not sitting on a differentiable manifold. So there are geodesics in these piecewise flat things, but they're, of course, if I take these literally kind of as classical geometries, they are, of course, highly non-unique, because they sit full of caustics, these objects. And then you imagine you have to take the continuum limit, then these caustics will actually become dense. So this is not the preferred notion. And if you look at the math literature, so actually I wanted to have maybe a conversation with you about it. I mentioned that this notion of optimal transport is, in some ways, can be sort of a substitute of this notion of geodesics. So it's other, if your geometry is non-smooth, there are other natural ways that people have discussed to characterize it. And geodesic doesn't seem to be, well, we can implement geodesic distances, but the individual path is not a very well-defined concept. You can smear it out. So people in 2D who work on the Brownian sphere and this, they have notions of geodesics which they pin down in two ends, and then you see it's kind of a smeared out cloud which narrows down to a geodesic. So you can do, at least in 2D, you can play such games, but it's not the most natural notion to work with.
Yeah, I was thinking the comparisons with a non-smooth Riemannian geometry,
Yeah.
and they also do singularity theorems there in mathematical theory.
It's
Maybe we can-
interesting, but they have a notion of curvature here, which uses a different terminology. So what actually, does that give me a new way of maybe thinking about singularities in a UV regime? Yeah.
Okay. This is, I think, a very short question. In your curvature calculations, are you looking at curvature averaged over the whole
Yes.
space-time, or have you thought about what happens if you look at a constant time slice,
Yeah.
where that might give you some information about what the time actually means?
Yeah, so, yeah, very good question. So, of course, this was skipped in the density information, and I didn't talk about it. Obviously, so I have this, kind of non-local, the two-sphere characterization of Ricci curvature. So that, again, is not an observable because it's just located in a specific point in space-time. So to make an observable, what I talked about, these curvature profiles, I sum over all pairs of points, and in that process, of course, I lose directional information. So what are natural ways of retrieving information? I could confine myself to spatial slices. Here, one has to be careful because these spatial slices in this discretized framework, they shouldn't be taken too literally. This is like, and also I think in QFT, you have to smear them out to get more physical things. But a more natural thing we are currently looking at is actually when you have a point mass in there, which has a trajectory, a space-time path, you can, of course, distinguish Ritchie curvature along and perpendicular. So that's actually a 4D project we are working on, where then this directionality would be made good use of, hopefully. Yeah.
I'm also very impressed by the Ritchie curvature things, because I think that's a handle of sort of connecting between a more continuum approach way and this arguably most close to the Planck scale, a non-perturbative way. So I'm interested, first, what the Ritchie curvature, it's really the Ritchie scalar curvature of your space-time.
Yeah, well, again, there was, I skipped information. So in this picture you saw, of course, there is in the continuum picture, there is a connecting vector in the direction between the two centers. So the Ritchie curvature, if I do the analysis on a classical Riemannian manifold, I said I can just do an expansion. So what you will find is, of course, the Ritchie curvature associated, is Ritch, RIC, associated with that direction. So it's basically, it's G mu nu downstairs, R mu nu upstairs. So that's what one finds, and that is associated with that direction.
And is it well understood in the math literature that it has no overlap with other curvature invariants, in a sense that if you have a Ritchie curvature flat manifold on which you have other types of curvature, that this measure is not affected? Or is it some overlap of all sorts of curvature invariants?
Well, of course, in the Riemannian case, if you just do the expansion and you see that as a quadratic order correction terms, you find both the Ritchie curvature associated with that direction, but you also find scalar curvature parts.
Okay, so it's some overlap of a bunch of curvature invariants.
You could say that. I would say, of course, on the lattice, as you know well, this fine-grained amount of detail can absolutely not be distinguished. But it's curvature, it's Ritchie curvature, it's Ritchie scalar already in the continuum. Yeah, but I think finer grains, even of course, it's not tensorial information, but of course we have a partial directional averaging is contained in the
Okay,
so I'm not completely sure I understand.
Let's continue this.
Yeah.
We have time for one more short question.
Yes.
Thank you, Renata, for a great talk. One thing I think is exciting is this potential for early universe phenomenology. In particular, it seems to me that let's suppose that in the future you can show that there is some emergent homogeneity and isotropy, but then you also have a handle then on characterizing, even quantifying the perturbations around that. And that would give us, that's an opportunity which I think all people working on quantum gravity should hope for, which is to provide an explanation from quantum gravity itself for primordial density perturbations, which for now we have to rely on inflation to provide for us. But that's, I think we should all hope that it's not inflation and that there wasn't any inflation, because we would like to have as much cosmological data as possible for ourselves to explain. So anyway, this seems very. Do you have any comments on that?
Yeah, the dream is, of course, indeed to provide, to derive from deeper quantum principles kind of the initial state, for inflation. And of course, as you're saying, of course, the two-point function of spatial slices are, of course, is basically, that is the power spectrum. Of course, this is a very, very quantum fluctuating regime. So a priori, we don't know. It may just be very, this homogeneity may be very, not quite there, but even that might have potential implications to say, hang on, everyone, believes this is just beautiful de Sitter with some tiny little quantum wiggles on it. No, but here we have something that has maybe, some specific but much larger fluctuations. What implications would that have? Thank you for the comment. Yeah.
Okay, thank you everyone for the questions, and let's thank our speaker again and come back in 6 minutes.
this is the top.
Right.
No, no, no.
You can insert it. That's
Can
sufficient.
be nothing else. There's no other
Ah,
information.
fine.
Like that? Okay.
You have to determine, you have to determine, yeah, so, because there are many expansions of these, looking at these wall volumes, yeah, this is classic curvature calculations, which is tailored. One through the order of every power series, the second order. What is special here is that we have Ritchie, so we have direction.
You've got to make that title the enigma.
The cosmic enigma of perturbative AQFT. Missed opportunity.
For the full, you mean outside? Yeah, it's in the vacuum space. Yeah.
All right, welcome back for the second talk today. Kasia Reisner will tell us from York University, will tell us about perturbative algebraic quantum field theory on causal sets. So,
Thank you.
please go ahead.
Thank you very much for inviting me to this conference. It's a great pleasure to be here and to listen to all these very interesting talks. So as you can see, I'm a mathematician. This is a very traditional Blackboard talk, mostly because I wanted to be very pedagogical and kind of give you an outline of the framework I'm working in. So this is, I hope this is very basic. If it's not very basic, please ask questions so I can explain it more. Okay, so algebraic quantum field theory, that was actually mentioned more than once during this conference, which is unusual. So here is just the sort of basic idea behind it. This was a framework which was invented in the 60s to axiomatize quantum field theory. So people felt that quantum field theory was a bit of a mess. There were divergences and so on. So that was an attempt to try to formulate the axioms and sort of build mathematical framework where quantum field theory lives. Okay, so this goes back to Haag, Kastler, Araki. Okay, so ancient history. So the idea, the original idea, was that you take regions, bounded regions of Minkowski spacetime, so Minkowski, okay, and then you assign to them algebras, okay, A of O, and this is interpreted as the algebra of observables that are localized in that region. Okay, so this I should say bounded, okay, and this is observables localized in O, and originally, again, these words were already mentioned, these were C-star algebras or von Neumann algebras. Actually, there are two sort of equivalent formulations of the framework. So one is C-star algebras, and the other is von Neumann algebras. Okay, and now, of course, you know, there has to be some axioms that these algebras have to fulfill. So that's the whole fun of algebraic quantum field theory. So let me give you three. I'm not going to give you all of them because not all of them generalize to the setting I want to talk about. So the first one, very basic, if you have some notion of a subsystem. So if you have a smaller subset inside the larger one, you expect to measure more observables. You expect that there's more observables localized say, in Bangalore than just inside RRI. So if that's the case, then this should also be the case. So there is an inclusion of algebras. This is an algebra morphism. Another one, and this is actually the most important one. This is what makes it kind of very Lorentzian and so very sensitive to causal structure. This is something which in my community we call it locality, but it's not what some other people mean as locality. So face it that some people mean one thing, some people mean other thing, and sometimes the same person means different things depending on the time of the day. I'm a bit like that. So there is one locality related to what I'm just going to talk about here, but I'm also going to mention other notions of locality. Locality is very overused. Therefore, we typically call it Einstein causality, just as a disambiguation. Okay, also known as locality. So let's say I have regions O1 and O2 that are space-like separated. So this symbol means space-like. Okay, then what? So I want these algebras that live in those two space-like regions to be independent, to not know anything about each other. So that's causality. So this means that A of O1 commutes with A of O2. And okay, where does this live? Well, this lives in A of O3. So sorry, this is equal to 0, where O3 contains both O1 and O2. O1, O2 in O3. Okay, so that's super important. And finally, and this is related to dynamics somewhat, there is something called time slice axiom. Okay, so yes? Yeah, sorry, that this is 0. That this is 0. I mean, I'm a mathematician, so it's a set containing only 0. But if you, yeah, I can do this, if that makes more sense to you, even though it's not strictly correct. I can make compromises. Right, is it clear now? Right. Time slice. So let's formulate it this way. So if I have what people call causal diamond, and I keep on calling double cone because, again, ancient history. So if we have a causal diamond and consider a Cauchy surface inside it. So, but yeah, actually it works for any subregion. Oh, I just like drawing causal diamonds. So if we have O in M, and we have a Cauchy surface going through here, okay? So we can restrict it to just living inside this causal diamond. Okay, so this is a sort of domain of dependence, right, of this Cauchy surface. So we somehow expect the information about the algebra of this whole region O to be reconstructed from the neighborhood of my Cauchy surface. This would be true for classical theory if we have initial value problem well posed. Now that is actually too singular, so let's take a neighborhood, okay, and I get the colors, so I can draw it in a different color. So this is N, N for neighborhood. So I know that A of N, of course, is contained in A of O because it's a larger region. Look at point 1. But the time slice axiom says that A of N is actually equal A of O. Okay, so this is Cauchy surface. Ow, sorry. All right. Now, there's more, especially, you know, I haven't talked about states at all, so there, yes, question? Yes.
So point one, then it should not have been a strict inclusion when like the AO1 strictly contained.
It's just contained. It doesn't. It's not non-equal. It's not strict. It's just inclusion. Yeah. Okay. Any more questions? Yes. Sorry. What is space-like separated? Sorry, I didn't understand the. I don't hear so well from that end of the room.
So in the second axiom,
Yeah.
O1 and O2 are space-like separated.
O1 and O2 are space-like separated.
Then,
Yeah, that's what this symbol
then
means. Yes.
The first one is O1 is a subset of O2. So how do
Yeah,
we get?
these are different. O1 and O2.
Oh, I see.
I could use O3 and O4. Okay. These are just any subsets. The labeling does not matter.
Just a quick question. In
Yeah.
Axiom 3 is the statement that this is true for any neighborhood or that there exists a neighborhood?
Oh, for any neighborhood. Yes, yes. For any neighborhood. Could be even a very large neighborhood, but then it's less non-trivial. Okay, great. So now this is all in Minkowski. That's a bit boring because we know, more exciting spacetimes than Minkowski. So let's generalize it. So this is all, as I said, 60s. Okay, so actually 1964 was the first formulation of these axioms. But now we want to apply it on curved spacetime. So we want to be able to do the same thing, say, on Schwarzschild, on De Sitter, or whatever. Somebody pulls out some spacetime out of their basement and we want to build quantum field theory on it. Yes? Yeah.
Just an
Yeah.
explicit example. So if you were doing, say, free scalar field on
No, I'm
Minkowski
not going
spacetime.
to give an explicit example
Okay,
because
no, just for that-
the second part of this talk
Right.
is going to
No,
be construction. So let me do it later. Yes, but your
Okay.
question.
No, so just for number 3,
Yeah.
what would it be like for example, for free scalar field on
Yeah,
Minkowski spacetime?
I
What would
will
it be?
explain exactly that. So I
Okay.
think that will become more clear how these axioms are satisfied and why. So let me refrain from that at the moment. Anything else? Okay, so let me move on. So generalization, first of all, I want to replace this. Replace with M, which is, well, I have to assume something. I assume my spacetime to be globally hyperbolic. So replace this with M globally hyperbolic. Okay, so which means that essentially M is a Cauchy surface cross R. That's what it means. You can see it's non-compact because R is non-compact for, well, it's not. So that kind of messes things up a bit later. And another thing, so this is to do things on curved spacetime. Another thing, there is actually a bit of embarrassing story about those C-star algebras and von Neumann algebras, and I mentioned that already yesterday as a comment. We don't know how to construct models of this type, even on Minkowski spacetime, using C-star algebras and von Neumann algebras, models that are four-dimensional, okay, like our world, interacting, so it's not just free fields, and satisfy all the axioms. That's very non-trivial. We haven't succeeded in doing it yet, and we've been trying a long time. Now, that motivates, yes? Yes.
Your time slice
Yeah.
axiom, I have often seen as a property of the von Neumann algebra.
It's not a property. It's
It
an
is not a
axiom.
property.
It's an axiom. Yeah. I mean, it's it comes with the package, right? If somebody says, let's take AQFT on Minkowski spacetime, that's in the package. So, that's, well, that's what one needs to, say, verify in a concrete model. But it's not automatic. It doesn't come for free. Okay, so I'm going to now go to the perturbative bit. So perturbative, what we have started doing in the 90s and are doing up to now, we developed a perturbative version of this framework. So replacing these C-star algebras and von Neumann algebras, which were great, I love them greatly, with something which is more compatible with, say, constructing gauge theories or even perturbative quantum gravity, and can actually apply to reality. So this we replace with star algebras. Okay, and moreover, we want them to be formal power series in H bar. Okay, so we will forget the question of convergence and just work with formal power series in H bar, which is actually useful because, I mean, in the end, if you want to just compute the quantum correction to, given classical process, you might be happy with, just computing various orders in H bar, which sort of in particle physics terminology is one loop order, two loop orders, and so on. So this is sort of more practitioner's viewpoint. And we are taking this on board, and we are going to formulate our mathematical theory in those terms. Okay, so now finally on causal sets. Okay, so now the question, which was actually very recent, it came to me after discussions with Faye and Sumati and all the wonderful people from the causal set community. Can one do this on causal sets as well? And my answer was, yeah, sure, but then somebody had to do it. So I have done it with my collaborators, Chris Fuster and two of our undergraduate students, Edmund Doubleheath and Nick Woods. And we have shown that indeed one can formulate this type of axioms on causal sets. So here, even I need a ladder. So replace now M with a causal set. C. Okay, so let's see what goes and what doesn't. This should go, okay, because we can talk about a subset of a causal set. This should, well, I mean, this has to be a bit modified, but we have the notion of causality, so we actually can talk about points being causally disjoint. So this goes. Now this doesn't, okay? Because there is no really good notion of a Cauchy surface. This gets a bit messy. So this doesn't work for causal sets. But that's fine. We can manage without it. So it does not generalize. Okay, I mean, one can try to cook up some notions of Cauchy surfaces, and again, I'm referring to my colleagues who are experts in this subject, but yeah, it doesn't really make sense to impose this axiom. Okay, now when we have this playground set, I'm going to go straight into constructing models. So I will work with this yellow and green generalizations. So I will first, or actually in parallel, I will show you how to construct these models, interacting models, on curved spacetimes, which you might find useful in its own right. And in parallel, I will show how this works on causal sets. Okay, time to erase the board. Yes. Yes.
before I erase it.
Including interaction is same as doing deformation quantization is what you mean by that?
Yes, yes, only, yeah, a bit more infinite dimensional than that. But yeah, there is a step which involves deformation quantization. And yeah, I guess in finite dimensional setting, we know that Poisson structures can be quantized. You know, there is Kontsevich, I mean, Kontsevich's result. But in infinite dimensions, this is a bit more put by hand. Yes?
Also a quick clarification.
Yes.
In the green version,
Yes.
you're not insisting on globally hyperbolic causal set.
Yeah.
It's any causal set.
Any causal set. Yeah, any causal set.
Thanks.
Mm-hmm. Yeah, okay, continue. Like, I mean, yeah, I guess. Yeah, I would ask this question back to Sumati, because it would work on anything where I could construct the green function on some discretization of the D'Alembert in terms of model building.
A quick question here.
Yes.
Since you're keeping the axiom 2
Yes.
in the usual framework, the space-like separated events are obtained using the Minkowski metric. Now, in the causal sets, as I understand, you have a notion of before and after. But how would you separate, demarcate, separate, even though they could be before or after, but they could still be causally disconnected?
Okay, so let's say we have this type of causal set. So this one is space-like to this one. Okay? So it doesn't, yeah, I don't know, is there some causal set name for this? I mean, for... No relation. Yeah, yeah. Oh, yeah, I think that's maybe the best way to say it. Thank you. Yes. No relation. Mm-hmm. So yeah, so for example, this pair of points. Does it make sense? Yeah. Okay, thank you. Okay, so I will erase the board. Can. Yeah. Yes, it is a bit like that, yes. Mm-hmm. But the fun thing is that somehow, yeah, it's a good test run for this theory, because nothing diverges, so you don't have to worry about it. And if you did something wrong, you immediately see it. So, yeah?
So if I may ask a very simple question. So before you go to causal set, so suppose you put this structure in curved space-time.
Yes.
And one ordinary curved space-time manifold, and try to get, let's say, something like generalization of spin statistics theorem or something. I mean, even in ordinary curved space-time, is it possible to find a consistent structure obeying all these axioms?
Of course.
It is.
I'm going to show you.
Okay.
Okay, so here is an example, running example. So scalar, well, actually, let's maybe do the general thing, and I will do the scalar thing in a second. Example construction. Okay, so first thing, I need a manifold. Okay, on one end, and it should be green. On the other side, with causal sets, I need a causal set. And this is globally hyperbolic manifold. Okay. Next thing, I need to specify what fields I'm going to consider. So on this end, this is specified by something I call configuration space, which is the space of sections of some bundle over M. So this could be scalar fields, vector fields, tensor fields, whatever. And for example, I can have E smooth functions on M for the scalar field. Scalar field, okay, on a causal set. And let's take a finite causal set. So let's take cardinality N. So here we know how to do scalar fields. The rest is still a bit iffy. So what replaces that? E is just Rn. So maps from N to R is just Rn. Okay, and now on this I will build observables as functionals on this space. So observables. So in the first instance would be smooth functions on E valued in complex numbers, okay? So here it becomes really infinite dimensional and rather ugly. Now here it's actually pretty straightforward because I just have smooth functions on Rn, which are pretty well behaving. Okay, so this is the basic setup. And now let me run along a bit with the left-hand side of the board, and I'm going to, well, talk a bit about these observables. So first of all, taking all smooth functionals on this space of configurations is a bit crazy because most of them are really wild. And also, we might, for some reason, be interested in local observables. And now, okay, now it's the different notion of local. Well, I guess another notion of locality is that, you know, in particle physics, we have local interactions, right? So interactions at a point. It's a different notion of local to what I just said. But this corresponds to taking local functionals in a very silly sense. So local functionals. Okay, so F log. I'm not good. Yes? No, yes, of all scalar fields, yes.
So here this infinity RMC is what is script E, or maybe I misunderstood.
This is, I mean, E is always E. I have terrible handwriting, but this is the same letter in the ideal world.
Sorry, what is the infinity RMC? What's the, so the space of all fields is RPD, and that's the configuration.
Yeah, so these are maps from causal sets, so from N points to R, which is also known as Rn. Yes. So it's really silly. It generalizes beautifully. Okay, local functionals. And again, so here, I'm just going to divide this as well. It's easy here. I would just define it by example. So f of phi is an integral of some function, say alpha, of the kth jet of phi. Okay, I will explain what that is. This is alpha, d mu of x. This is some measure, well, the invariant measure. Sorry, let me just explain it and then I will tell you. So j k of phi at point x. This is the value of the field. And then you go with the derivatives up to order k. And now I can take question. Sorry? Yeah. Is it clear now? Okay. And here, do you see when I write here? Okay. So, sorry, what is what? It's a field, sorry. Phi is an element of E, thank you. So an example would be, say, phi to the fourth. It's almost a good example. I need to smear it with a test function. So Again, I'm running out of space a bit. So f is in smooth, compactly supported functions on M. Okay, so these are typical local functionals, right? Like phi to the 4 of interaction is a typical local functional. Here it's a bit more tricky. So first of all, let me define a product on the space of vectors and vectors, which is not the right product. It's you know, when my students start learning about matrices and matrix multiplication, the first thing you do before you learn how to do it properly, you kind of try to multiply each element with of one with each element of the other and see what happens. So that's actually, that has a name. It's called Hadamard product. So it has probably nothing to do with the Hadamard state. I don't know. Do you know? Hadamard product. Okay. So if I have phi, which is, well, let's write it explicitly in Rn, and psi in also Rn, then phi product psi is, okay, so phi 1 times psi 1, phi 2 times psi 2, and so on, phi n times psi n. So I just multiplied them like this. This is not how people deal with vectors normally. But this is actually the right product if I want to find an analog of these objects. So here, local, and now I'm using quotation marks because this, yeah, here we are a bit losing this idea of, well, localization at a point. I mean, things are a bit wild, but the direct analog of these guys are of this form. So we have, well, instead of integral, we have a sum, I equals 1 to n. Okay, so here, let's do phi to the 4th because it's a nice one. So we take an Hadamard product of 4 of these guys. Okay, and here I was smearing with a test function, so you can also do that. I, Fi, where f is also in Rn. Okay, so this will become useful when I start talking about interactions. So in both cases, you know, I will start with the free theory, quantize the free theory, and then introduce interaction perturbatively by adding to my original action terms like that. Yes?
So you said so far this works for general. So far this would work for general causal set.
Yes.
Because before you said, well, probably at a later stage you need nice causal sets. So I'm
so
I'm
at the
waiting for
moment,
some nice
yeah.
Regularity definition.
At the moment, niceness was not
provide.
needed. Niceness will be needed soon. So, yes. Yeah.
F1 could be 1 and all the other F0. I mean, there is a...
It could be stupid, yeah. Or could be everything 1.
Yeah,
F could be everything 1, yeah, if I want to. Yeah. It could be localized at the point or everywhere.
I have a question. But why do you have 2 different index placements here for I? I mean,
why do I have to what?
2 different placements for I.
Oh, there is no reason. I mean, this way I kind of keep track of what's a row and what's a vector, but it doesn't have a meaning. It doesn't have a meaning.
So as with many things that are order theoretically defined, it will work for any causal set until the point where you perhaps need to construct something that compares with a continuum. So then when you do that, then as Kasia said, need for a green function. We know certain cases where you can construct something that, but defines perfectly well in every causal set. So this is kind of the thing. But if you want to make a continuum comparison, then those continuum comparisons are only possible when you know what that green function.
Yeah, I mean, more things make sense mathematically than they make sense physically, I guess. That's always true. Nothing new there. Okay, so now let's do free scalar field first, as promised. So free scalar field. Okay. So I start with equations of motion. Okay, and for space-time, this will be given in terms of D'Alembert. Okay, and this thing here is the Klein-Gordon operator. Now this type of an operator, sort of wave operator type, this has a name, so this is in particular an example of a normally hyperbolic operator. Normally hyperbolic operator. Okay, and for such operators on globally hyperbolic spacetimes, there exist unique, and this is important, retarded and advanced green functions. So green functions appear. Delta R and delta A, retarded / advanced green functions. Okay, and here on the causal set, and this was already mentioned, and Sumati can tell you much more about. There is the work of Sumati, Fei, and Norman, I think. Tell me if I'm missing some people. So here we also have, well, I mean, you can actually discretize this operator. So one thing would be discretized and discretized. Oh, okay. So I'm just going to do the green divide. So here, discretized P and causal set.
Raphael and students of Raphael and in 2D, and then later by Stephen Johnston.
Okay, but that was about the states. So let me
no,
also about that. Okay,
function,
okay.
The 4D
So
flat green function was Stephen Johnston.
so
we
Sokin,
generalize it to De Sitter.
Johnson. More people. So yeah, so this is actually, I mean, I walked into this when all this has already been done, which means that, you know, I was very happy to see it, because that's essentially all I need to quantize a scalar field, is to have this retarded green function. Okay, so why is that important? Well, first of all, I'm going to define classical theory, and I'm going to do it in terms of a Poisson structure. Again, mathematician. But it's very similar to what you would do in classical mechanics. You know, I also teach that to students. You have functions on the phase space, and there's a canonical bracket, right? This is a Poisson bracket. So you can formulate classical dynamics in terms of a Poisson bracket. Well, here, actually, there is a covariant way of doing it, which goes back to Pius from the 60s, again, ancient history, which was used sort of in parallel by my community and also by Raphael and others in the causal set community. Yes?
We know that the Klein-Gordon equation with the mass term
yes.
is covariant under Lorentz transformation.
Yeah.
Is there a similar symmetry when you go to the causal sets?
Yes, yes, but I mean, this is all fully covariant. It has to be fully covariant because you don't, yeah, I mean, first of all, you don't have foliation into Cauchy surface, right? You don't have a time direction. And second of all, I mean, causal sets are built this way, that this is Lorentz invariant formulation. So yeah, I send you to these works. There it is discussed in details, very nicely written. Yeah? Yeah, well, it was, yeah, okay, but it was Pius who formulated the bracket, yeah. So, no, I'm not talking about QFD, I'm talking about classical theory. Let's give it to Pius. He deserves the credit. but yeah. Okay, so Pius bracket. Okay, so first of all, let's define something which, well, it's called Pauli-Jordan function, but it doesn't matter how it's called. Pauli-Jordan. And I don't know if it was invented by Pauli and Jordan, because these things are sometimes confusing, which is the difference between retarded and advanced green functions. And now the bracket of two observables. So let's take fg in f log. This is defined as, okay, so I take variation of this, the f over d phi of x. Then this, as a green function, has two slots, two arguments. Is actually a distribution, not a function, but who cares? I'm just not going to care. I'm going to insert it here and then contract the other guy as well, okay? And then integrate everything d mu x, d mu y, okay? It's covariant. It is, yeah, so, also another thing I should emphasize for people who care about that, this is all happening off shell. So f and g are functions on the whole space of field configurations. There is no, I'm not restricting to solutions to equations of motion. Okay, so this is off shell. Okay, and the causal set version, that's also very easy. So remember, f and g are now functions on Rn. So now we have some ij df over d phi I. And now this is a matrix ij dg over d phi j. And phi is again an element, well, let's write it explicitly here, of Rn. So that works. Okay, now how to quantize it, and this is where I'm coming to Aluk's questions. Finally, something quantum, right? I'm using the idea of deformation quantization. So let's leave the classical story here. So this may differ from what you're used to. Deformation quantization. Yeah. Oh, yes, it's antisymmetric. Yes, yes. That's a very good point, because dxy is equal to minus dyx. Okay? Maybe I should have said about the, it's maybe not entirely obvious to people what are retarded and advanced green functions. So they are distinguished by these support properties. So if I have a test function supported somewhere, and then I apply a retarded green function, then this is supported in the future of this support. And if I take advanced green function this is supported in the past. And these guys are uniquely defined by these properties. So this is okay. So causal structure is important. Deformation quantization. So I'm looking for a star product on, well, some space of functionals, nice space of functionals. Okay, containing local ones. Formal power series in H bar, such that, so first of all, when H bar is 0, this should give me the classical product. So F star G at H bar equals 0 order, that should be F dot G. So this is just classical pointwise product. Okay, and then second one, something about commutators. So, okay, let's do 1 over I H bar. And now let's take the commutator of F and G with this star product. Okay, so the 0 order cancels out. The first order, I'm here taking 1 over IH bar. So this now at the lowest order should be the bracket. Okay, so Poisson brackets go to commutators. And we are talking free scalar fields, so actually this can be done. One can find such products easily. They come cheap. And an important notion for finding such products is that of a Whiteman two-point function on Minkowski or two-point function of a Hadamard state on general spacetimes. So here, I'm going to take an object called delta plus, which has my Pauli-Jordan function as the antisymmetric part, plus some symmetric piece. Okay, and I'm going to require some properties for that. Okay, so such that. Okay, so first of all, I want this to be of positive type. This is supposed to work as a two-point function of a state, so should better be positive. So as a distribution is of positive type. Okay, 2. There's a condition on singularity structure. It's a distribution, it's singular, but I want it to be as singular as the Whiteman two-point function in Minkowski vacuum. So singularity structure is that of Minkowski vacuum. Vacuum two-point function. For those people who are, familiar with this, this is the spectrum condition, microlocal spectrum condition. And the third one, okay, I also want this to be a solution by solution for my equations of motion operator. So Px delta plus xy is 0, and it's also Py delta plus xy equals 0. Okay, so with these three, an object which satisfies these properties and has also this antisymmetric part, this defines me a two-point function of a Hadamard state. And this is where things slightly diverge from the causal set community. So here, these Hadamard states are not unique. So on a given space-time, there is typically a plenty. Okay, there is no distinguished Hadamard state. But nice states that we are interested in for physical reasons tend to be Hadamard. So it's actually not a big restriction. Yes? Oh, this was the Klein-Gordon operator. It was on the previous slide. Yes.
So in standard quantum mechanics,
yes.
the quantization F is not same as the classical F. Classical F is
Yes.
function, while quantum F is an operator.
Thank you for that question. Yes, so this is not standard quantum mechanics. So this is an approach to quantum mechanics as well, called deformation quantization. So in this approach, you construct your algebra of, well, operators, okay? You construct it abstractly, not as operators in a Hilbert space. And you specify it by introducing a product on a vector space, okay? So the vector space is the same as the vector space of classical observables. The product is different. So the same exercise can be done, say, for a free particle in quantum mechanics. And you will see that this is exactly equivalent.
So F and G, they have the same meaning both in the classical
correct.
And the quantum.
Yeah, which is actually a good thing in many ways, because if you commit to your observables in the classical, say, I mean, these are simple examples with the scalar field, but if you're doing gauge theories or perturbative quantum gravity, you might have some complicated non-local even things, right? So you have some crazy relational observables or dressed observables or whatever comes out of your head. You write it down in the classical and check all the properties, and then you carry them over to the quantum, just changing the product. So that is actually a feature. Yes, yes.
Actually, I thought one of the issues with deformation quantization is if I take two-dimensional sphere and just do a...
That's geometric quantization. This is formal deformation quantization.
I mean, if I just take two-dimensional sphere and do a deformation quantization, the algebra I get is the universal enveloping algebra of SU2, and then I don't recover discrete angular quantization unless H bar takes discrete values. So
okay, but this is flat. This is free scalar.
Deformation doesn't give the physical quantum mechanics unless we discretize H bar.
We have to talk about it. I mean, there is a nice book of Stefan Waldmann, unfortunately in German, where he discussed these points. But yeah, let's talk about it during the discussion, if that's okay, because that's a very technical point. Right.
Is there any point actually on the left part of the following the first point on the left?
1, 2, 3.
No.
Yeah.
Example. I'm interested in the properties of star. Specifically, whether this is associative product or not associative.
Oh, yeah, it's associative. I should have added, yes. Thank you. Associative. Yeah. I was taking it. It was associative in my head, yes. Right?
I can't read your writing. Is that I over 2 delta?
Yes, sorry.
There should be an I there.
Yeah. Good. So let me now quickly remark on the causal set part of the story. So this, again, carries over to the causal sets. So this generalizes. So generalizes. To causal sets. And this is the work of Raphael Sorkin, okay, and his student Johnson. So actually, this was the Johnson thesis. So this is the Sorkin-Johnson state. Okay, and this the difference here is that this is actually unique. So delta plus would be unique pair causal set. So this is unique. Well, well, on causal sets, it's not a notion. Yeah. Yeah, but but then there is. So we have shown with my student actually that there is like a smoothing procedure that Raphael suggested, that you can take the Sorkin-Johnson state in the continuum, but introduce some smoothing. So you just have to smooth it a bit out on the edges, and then you can recover family of Hadamard states that depend on the choice of smoothing. So again, you lose, it's always a trade-off. You lose uniqueness, you gain Hadamard. So, okay, so that's the free scalar field almost done. Let me now write down this product. Okay, so I introduced this delta plus for a reason. So I define F star G is, okay, so going to be an exponential H bar. And here, okay, I'm using a notation for kind of contracting with a distribution. So I will differentiate the, I'll write it larger so people can see better. D phi 1, D phi 2, apply it to F of phi 1, G of phi 2, and here I set phi 1 equals phi 2 equals phi. Okay, so this should be F star G of phi. Okay, exercise for the audience. You can check that for Minkowski vacuum, this actually gives the same commutation relations as per usual. We can talk about this exercise later. So that's now the algebra. So I have a product, right? That's the algebra of the free theory. Yes.
So this field bracket is the lowest order, right?
It has yeah. I mean it has all the orders in H bar. Oh, sorry. The Pius bracket is, yes. It's the first order in H bar. Yeah.
So the generalization of that would be something like the Moyal bracket.
Oh, this is the Moyal product. This is the Moyal product. Yes. Again, it's borrowed from deformation quantization. I'm leaving this delta plus here for a reason. Okay, so now I want to do interaction. So let's do interaction. And for that, so, okay, the term S matrix was also used in many ways. I'm probably going to mean something different than everybody else. But you know, morally speaking, if you want to introduce interaction perturbatively, one way, which I think people use a lot, is path integral, okay? So I'm going to do path integral, but sort of in an algebraic way. So I'm not going to think about it as an integral. I'm just going to think about it as a map from observables to complex numbers with some properties, okay? So I'm going to completely encode the path integral combinatorics and all the information that's there in appropriate definition of the time-ordered product. So if you have done QFT sort of, you know, at school, in the kindergarten, they teach you about like writing the S matrix and expansion into time-ordered products. So I'm just going to extract that out of my textbook. I'm going to try to make sense of that time-ordered product. So for that, I also need the Feynman propagator. Let's not make too much of a mess. I'm going to write it here properly. So that was, okay. So I had this delta plus, and now I define the corresponding Feynman propagator as I have delta retarded plus delta advanced plus h. So it only differs from delta plus by this sign, okay? Now, so you see the whole glory. This was delta retarded minus delta advanced, okay? And this sign, the fact that they have plus, means that singularities do not cancel at the origin. So this is very singular. This is very ugly. Okay, this is a matter of taste. It's beautiful in its own way, but can be very scary if you're not expecting it. Okay, so now I define a product using this, and this is my time-ordered product. Okay, so this is the same formula, all right, but here I'm using Feynman propagator, okay? So the same f phi 1, g phi 2, and here phi 1 equals phi 2 equals phi. Okay, so that is called the time-ordered product. Okay, okay. How much time do I have? 5 minutes, great. So this doesn't work as I wrote, unfortunately. It doesn't work if f and g are local and not linear. Because if it worked, then all this enterprise of renormalization would be completely unnecessary and superfluous. So this has to be actually fixed. So let me put it in red. So not defined on local functionals. Let's say local nonlinear functionals with overlapping supports. So as long as f and g don't have overlapping supports, this is fine. If they have overlapping supports, then this needs help. And that help is called renormalization. So this needs to be renormalized, and there is actually, again, established piece of mathematics and physics that does that. So it's called Epstein-Glaser renormalization. So needs Epstein-Glaser renormalization. Okay, so that goes back to the 70s. So we moved one decade ahead. Okay, so but assume that somebody has done that, so I don't have to do it. This can be fixed. So morally speaking, it should be that, but these products of Feynman propagators have to be fixed. Assuming we have that, we can now define the S matrix, or actually formal S matrix. Okay, so given V an interaction, define
S of V is the time-ordered exponential. So just exponential, but you use this time-ordered product, I over H bar V, okay? And also, we can define interacting observables. And this is the last thing. Observables, one uses slightly cryptic notation. RV of F is an interacting observable corresponding to F, an observable F. So this is T I over H bar V inverse, star inverse. T inverse would be silly. Star ET I over H bar. This is also I. It's hard to see those I's. Yeah, no, just let me finish. Okay, good. Thank you. That's the end of the talk. Yes, yes. T, oh, okay, so I can explain it again. T is the time-ordered product. So I can actually write it. So ET of V, right? So this would be 1 plus V plus 1/2 V, and so on. Okay. I can also give a summary since I want this bit of extra. Okay, so that is essentially it. I should also tell you that, well, from this point on, when we got this delta plus on the causal set side, everything else just runs on autopilot. So all these constructions work just as well on causal set. Actually, they work better on causal sets, because on causal sets, this is actually well defined on the nose. Yeah, right, exactly, because, of course, not defined, so defined on C, which is one of the reasons why I found it really useful to work with causal sets, because you can play with these algebraic structures and sort of, study the algebraic properties without worrying about, technical details like renormalization. I mean, this is interesting in its own right, but sometimes you just want to check if something is true in principle, and this is a good testing ground to kind of separate, functional analysis from algebra in algebraic quantum field theory.
But as I said, you are reducing the field theory to quantum mechanics, and so you don't want to worry about renormalization.
Yeah. No, but so I want to underline one thing, that it works with exactly the same formulae, the same structures. So we actually learn things about those structures by studying them on causal sets, because they are very, so when you're doing it in quantum field theory, right, some of the structural properties are obscured by the fact that, okay, renormalization is ambiguous and you have to, define those various extensions and so on. But if you're, say, interested in, say, deformation quantization, right? So you want to see if, so here is the formula for interacting observables. You can use it to deform the product, define the interacting star product. If you want to study the interacting star product, obviously it's a bit tricky to do it in the continuum, because you run into all this renormalization issue. But interacting star product is interesting in its own right, and you can actually study its properties on this toy model. It's good when sometimes you don't have to do all the hard work. Yes? Can we actually close the talk and then have questions? Okay, thank you. Just wanted to thank you for your attention, if this is okay. but people might have like quick questions. So, yeah. I don't want to cut off Alok.
So just a clarification with the formal S matrix. So this, as you say, V is some local functional V. But if I just look at the usual S matrix, it will be the interaction Hamiltonian in the interaction picture. Interaction picture.
No, I don't do Hamiltonians. This is all Lagrangian. So I would think of S matrix. Yeah. So I'm thinking everything in Lagrangian formalism.
Is there an interaction picture that you need to define V, or you don't
No, there isn't. But it is analogous to the interaction picture, sort of morally speaking, right? So yeah.
That's a very small question.
Yeah.
Usually when we do quantum field theory, everything will be done with time order product of correlation functions. Right?
Yes.
Everything is inbuilt. But here it seems that you need two independent products, star and T. So why do we need more information?
I mean, are you in Euclidean or in Lorentzian? You're in the Lorentzian. It depends what you calculate. So you just need the time-ordered product to get the green functions, the scattering amplitude, so to say. But if you want to compute correlators of interacting fields, then you need star product. You might not realize it because, say, in Minkowski vacuum, when you evaluate in a state, this factorizes. So this factorizes into two terms. So there's like state applied to that is the state applied to that times the state applied to that. So this becomes like a normalization factor. So you don't see it.
But everything is coming from finite propagator.
No, it's not. No, it really isn't. I mean, it might look this way because, as I said, when you evaluate in a concrete state, then things cancel out. But this is the operator product. If you're thinking about the Heisenberg, the interaction picture, then at some point you would have operator product of things. You can, yeah.
Yeah, maybe I can respond to Alok's comment. Is that one of the problems in the standard approach? One of the problems with standard interacting quantum field theory is that we get ultraviolet divergences because the point splitting that you do for products of operators that are at the same point is not does not respect Poincare invariance, and that is the observation of Epstein and Glasser. So if you do it right, as Epstein and Glasser have taught us, then you have no ultraviolet divergences at all.
No, I think Alok is worried about star product, but we can discuss it in private, or during the discussion I can show an example. Yes.
For the real scalar field, F into G is real.
Well, it doesn't necessarily have to be, but okay.
Because your delta plus or delta F is complex, does F star G, is it obvious that F star G would respect that?
No, it doesn't have to be real. I mean, we are, this can be complex valued.
All right, so the product of two observables, I thought F and G are observables.
Yeah, but then you evaluate it in a state. When you evaluate it on a state, you get a real number.
So there's another space of states? In quantum mechanics, I know, operators act on states of...
Oh, very good. So this is the, think about it this way. So in quantum mechanics, you have the Hilbert space and the algebra of bounded operators on the Hilbert space. In the algebraic approach, you have the algebra first, and states are functionals on the algebra. So are maps from the algebra to complex numbers. And from such maps, you can construct Hilbert space representations. So Hilbert space representation sort of comes later, and at that point you have all the properties you want when you evaluate things in a state.
Okay, thank you.
Thank you. Okay.
Can we all come down to the lawn? I'm going to check whether the photographer is there, and if he is not around, then we have lots of photographers here. And we're going to have an informal, formal conference photograph. Yes, selfies. But yes, somebody